Today we shall be dealing with AC power analysis. This is the entire sheet of AC power analysis, list of topics, subtopics, formulas that we are going to deal with. Let's get started with instantaneous power. This is the formula that represents instantaneous power, and it is instantaneous, steady state, and sinusoidal in nature. Voltage and currents at terminals are given by these formulas. Vm and Im here are amplitude and peak values, and theta v and theta I are the phase angles. Instantaneous power absorbed is given by this formula or this formula or this formula, depending upon what are the things given in the numericals. Okay, let's talk about if the power absorbed has a positive sign to it, it means the power is being absorbed. Otherwise, it is the power is being supplied. It is difficult to measure because it varies with time, so we use the concept of average power, which is measured in terms of watts. Let's talk about average power. It is defined by this formula in time domain. It is time variant and it can be calculated in both time as well as frequency domain. In instantaneous power, this thing can only be calculated in time domain, whereas average power can be calculated in both time as well as frequency domain. In phasor domain, we represent by these formulas. The average power is defined by this formula or this formula or this formula, depending upon what is the nature of a numerical and what data is provided in the numerical. Let's talk about if power is absorbed by a resistive element. This is the formula. Okay, you can use any one of it depending upon what is the data given in the numerical being asked. Let's talk about average power absorbed by a pure reactive element. Okay, let's talk about pure capacitive or pure inductive in nature. Here theta turns 90 degree and the power absorbed is 0 because cos 90 is 0. Okay, now let's talk about RMS value. It has so many definitions. It is measure of effectiveness of a voltage source in delivering power to a resistive load. It is defined on the basis of heating effect of the waveform. It is defined as that AC voltage at which heat produced in an AC circuit as well as DC circuit is same, provided that both the circuits have equal resistance and have been supplied for equal amount of time. And it is given by this particular general formula. And for sinusoidal waveform, this general formula converts to this formula. Let's suppose you have multiple sources of different frequencies, then this is how you calculate. Okay, let's talk about average power delivered. It is given by this formula, this formula, this formula, depending upon what is the nature of the numerical you are going through. Okay, the data provided in the numerical. Let's talk about RMS. It doesn't depend on position but rather depends on the shape of the waveform. Then we have a fundamental fundamental formula over here, which states VRMS equals to Vm by root 2, and this highlighted formula is something which we are going to use. Okay, an important thing to remember. PAV equals to VRMS IRMS cos theta V minus theta I. Let's talk about average value. It is defined on the basis of charge transfer. It is that AC voltage at which charge transfer in both AC circuit and DC circuit is same, provided that both circuits have same resistance and have been supplied for same amount of time. And it is defined by this general formula. And when it comes to integration, okay, if the waveform is symmetrical in nature, you are going to integrate to the half value of the waveform. If the waveform is not symmetrical, you are going to integrate to the full value. Okay, let's talk about form factor. It is given by this formula. Peak factor is given by this formula here, and these things determine the shape of a waveform. Okay, these two things are responsible for the shape of a waveform. Now let's talk about apparent power denoted by S, and it is measured in VA, which is a complex power denoted by this formula, and then we are converting it to rectangular form, so we are getting this formula, and the general format is P plus JQ, where Q is the reactive power and P is the average power. Let's talk about real power or average power, or P in this case, which is measured in watts. Okay, so this is the formula which we are going to use in numericals, and the phasor, in phasor format we have this formula. Let's talk about reactive power. In reactive power, it is also called Q here. Okay, and it is measured in var, or volt ampere reactive, and Q is defined by this formula, and in phasor format has this formula. P is the useful power and dissipated by the load. Q is the exchange between source and reactive part of the load, or the lossless interchange between load and the source. Let's talk about if Q is equals to 0, if the reactive part is equals to 0, then we are having a resistive circuit. It means theta V equals to theta I. Let's talk about if Q is less than 0, then we have a capacitive element. Okay, capacitive circuit or element, or whatever we are dealing with. Okay, then theta V is also less than theta I, means voltage lags current. Then we have Q greater than 0, or we have inductive circuit, and so is the case. Let's talk about complex power in terms of load impedance. So these are the formulas which we are going to deal with, and I cannot point out a particular formula over here because all these formulas will be used in solving previous year's questions paper. So I am not here marking any one particular formula. And let's talk about, means here we are trying to establish a relationship between load impedance, that is represented by Z, and also the complex power, means S. We are here trying to establish a relationship between S and Z. Okay, so these are the formulas we are going to use. The asterisk sign represents the conjugate. Okay, keep that in mind. Then we have P equals to I square RMS into R. Q has this particular concept. Okay, let's talk about power factor. Power factor is this thing and has this particular formula, whereas theta V minus theta I is the power factor angle. This thing is defined as the power factor angle. Power factor angle equals to load impedance angle. Both of these things are same thing. Okay, theta V minus theta I can also be called as power factor angle or load impedance angle. They can give you any name. Now we have this particular formula, and if theta is greater than 0, it is lagging circuit, and if theta is less than 0, then it is a leading circuit. Let's talk about power triangle. Here we have apparent power, the real power, and reactive power, and we have things regarding this. Okay, we have, if the complex power is in the first quadrant, then it is inductive circuit with lagging PF. If in case the S lies in the fourth quadrant, okay, then it is a capacitive circuit and has a leading nature, leading PF. If S lies in both second or third quadrant, then the load impedances are negative. It means the entire circuit is active in nature. Active and passive elements we have discussed in our previous sheets. Okay, so go check that out. Then conservation of power is followed by both AC and DC. It is followed by P and Q, active power and reactive power, but this doesn't hold true for complex power. Okay, so this is all for AC power analysis, and take a look at the sheet. Okay.